Okay.
All right, that's our final talk of the day. So thanks again, everyone, for coming out. I hope you enjoyed it today. I'll make the introduction from up here. Hopefully I'm loud enough for everyone to hear. Many of you know Barbara Becker. She's given a few talks for us here at TriStar. She's probably my favorite visitor to look onto the speaker series because she and I have a lot of common interests in 19th century early astrophysics. And so if you've been here before, you've heard her talk about the Hugginses, and she wrote the book about William and Margaret Huggins. If you haven't read that, it's an amazing book. She's also talked about
solar eclipse expeditions.
About the Hugginses and their things at TriStar, but she also gave a great history of solar eclipses talk for us here in this room a couple of Aprils ago. But this time she's coming into not the current century, but just the past century, which for some of us to tell us about a very interesting thing. So if you're of a certain age, you remember the arguments about cosmology that went on in the 60s and 70s, and we're going to hear about that today from Barbara. So let me turn things over.
Okay, thank you. Thank you. Yeah, so if I lapse into talking about, say, like 1880, know that I really mean 1980.
Yeah, so make sure we got good sound on the
okay. Now, is this better? I kind of have to lean in. I'm not sure how to set this up here to make the keyboard. Is this good? Can everyone hear? No?
Yeah, so you advance on the keyboard here.
Yeah.
Okay.
Right. But am I?
I think she's in charge of it.
Oh, she's in charge. Oh, okay. All right. Now can everyone hear? Yeah? Yeah? Okay. Now, in the early 1980s, my father-in-law sent me some clippings from the Los Angeles Times. And it's all about battles with astronomers, among astronomers, and threats of taking telescope time away, and words like heretic and maverick and so on were in the headlines. And I was teaching introductory astronomy at the time, and so this was something that generated some interesting discussions with my students about how scientific communities deal with disruption and resolve things. How does it come to what our modern ideas are? And so this was in the 1980s, some 20 years after quasars became the problem that they were for so long. But things hadn't been resolved then at that time, so it was it's something that I followed for a number of years afterwards to see how things were progressing. But my interest was really rekindled in 2013. Oops. I'm supposed to be able to advance this with the... This isn't... Can we advance the slide somehow? That's what I'm doing. There we go. Okay, great. Oops. Yeah. There. Okay. In 2013, there was a symposium at Caltech to celebrate the 50th anniversary of Martin Schmidt's announcement that he had discovered the secret, the mystery, and resolved the mystery of the spectra of quasars. So Ken Kellerman, who was then at the National Radio Astronomy Observatory, gave one of the talks. And this was, in this, he started out with this first slide, the road to quasars. And here you see a kind of nice linear pathway of showing how we led up to this grand culminating event of the announcement by Martin Schmidt. So these were the steps that the technological and theoretical advances that were made over that period of time leading up to that. And then, of course, he was also perceived as the sort of launching point for the first steps in our direction of understanding and coming to our modern view on what quasars are. So it was really quite a wonderful and exhilarating talk to see all this wonderful information spread out before our eyes, and that path that was all very direct, very direct. And I'm sitting there listening, and I'm thinking, wait a minute, where's the blood? Where's the guts? Where's the controversy? Where's the heretics? Where's the mavericks? What happened to them? How did it come to be such a neat, orderly story after just a few decades? This kind of presentation is what sociologists call a scientist's account. And the scientist's account, illustrated here, you have a curious person, they find something puzzling that they can't figure out about the natural world, and so they do some observations, they do some investigations, they try some experiments. Each time they know exactly what to do next. Each time they find some kind of new information and they know exactly how to use it. And when they finally come to the answer, they know that they've found the right answer. And then they run through town in their birthday suit and shout, "Eureka! I found it." Now, it's interesting, this story about Archimedes didn't come into existence until 200 years after Archimedes died. So there was some time for this story to evolve. But these kinds of stories are not necessarily the real story of what happened, but they serve useful purposes. They help to legitimate the research and the work that scientific communities feel that they are undertaking. It sort of gives them a story, a mission, a sense of fulfillment. But it also helps to excite and recruit and attract and socialize new recruits to that discipline. So you know that you fit in. You're part of Galileo, you're part of Newton, you're part of Einstein. And all of those things are just one long, continuous, and you're the next step. So the scientist's account is really quite an interesting thing. But one of the downsides of the scientist's account is that it fogs the community's memory of what really took place. And so I think that the story about quasars is an interesting example of one of these stories that you can see through its development, all the little twists and wrong turns and detours that people made along the way. And I find those things to be really quite interesting, and the kinds of challenges that they presented to the community at large. So let's go back to the 30s and 40s. That's the 1930s and 40s, not the 1830s and 40s. But when radio technology, radar technology, was in its infancy, and astronomers started to realize, much to their surprise, that there were not only terrestrial sources of radio waves, but there were also celestial sources, confusing, mysterious sources that didn't seem to have any kind of visible objects that one could examine with a telescope to see, what was going on, take their spectrum and examine them closely. So here's an area that was first found by Grote-Reber in 1944, and he was in the constellation Cygnus. It was just named Cygnus A, and no one could find an object that they could identify that was the principal cause of this radio emission, this strong, focused radio emission. Now, a lot of astronomers at the time just assumed that this was noise going on within our own Milky Way galaxy. So it was a sort of a local event, a local cause, and maybe just sort of randomly distributed in clouds of radio emission or something. Now, Walter Baade was convinced that, no, I don't think so. I think these are extragalactic sources. And in fact, maybe because of the amount of energy that would be required, these are like galaxies in collision. So he was a lone wolf on that theory. But in 1951, he managed to capture an image of a very small but visible source, the optical source of Cygnus A's radio emission. And boy, it sure looked like galaxies in collision. And so it seemed to kind of give him a little confidence in his theory that these things are extragalactic in nature. But the best thing was that it encouraged other astronomers to really start looking more closely at these areas that seem to have concentrated areas of radio emission and look hard for their sources of optical information so that we could examine them more closely. So in 1960, Alan Sandage found one such object, 3C48, and it wasn't galaxies in collision. It looked like a star. It just looked like a star. He called it a radio star. And his colleague, Jesse Greenstein, managed to capture a photograph of its spectrum, which was great because now we've got data. We can try and make comparisons with other sources of information about their spectra. The only problem was that it just did not match anything that anybody had ever seen. And it was really troubling because they were trying to make some sense out of this. Here it is. It looks like a spectrum. It acts like a spectrum, but it just doesn't seem like anything we could identify. In 1962, Cyril Hazard in Australia captured an image of this radio source. This is 3C273. It not only looked like a star, it was a kind of a fuzzy-looking star, and it had this peculiar little jet sticking out of it that, stars don't have jets like that. It was quite bright, and Martin Schmidt was able to capture a spectrum of that object. And just like 3C48, no one could figure out what it was. It just looked so different from anything that anyone had ever seen. But with this spectrum, the lines were registered clearly enough that Schmidt kept thinking about it. For months he was thinking about what this. It looked somewhat regular, like there was a sort of a progression in the spacing. There's progressions in the spacing of spectra of ordinary common elements that we see. And so maybe if he conducted some investigations just taking ratios of the different spacings and see if it matched with anything. Now, I attended a lecture back in 1981 that Martin Schmidt gave, and someone in the audience, this was at Goddard Space Flight Center, and someone in the audience asked him, how did you come up with your solution? And he answered, it came to me in the shower. And so I don't know if that's a true, this may be a scientist's account, but you can envision Archimedes running through the town. But at any rate, his solution was that this was simply the hydrogen-Balmer series. The reason we didn't recognize it, it's so familiar to us, but we didn't recognize it, is because it was redshifted by 16%. This object, if we use the Hubble's cosmology principle, this object must be some 3 billion light years away. Now the problem was that anything that we knew, the brightest thing that we knew, if we were to throw it out 3 billion light years away, there was no instrument on Earth that could see it. It would be so faint it would be beyond our ability to detect. Not only that, when Jesse Greenstein went back and looked at 3C48 and looked at its spectrum and did the same process, assuming that it was the Balmer series he was looking at, he found that this object would have to be some 5 billion light years away. So what was up with that? I mean, is this something that maybe there's something wrong with our understanding about the redshift and how to calculate things and distances involved? Or are these objects so unusually luminous? Maybe they're closer by. They're just so luminous that we don't have any idea what kind of physics would produce something that could be visible with that level of luminosity at such terrific distances. Now, some of you may recognize this cartoonist. Sid Harris is known for his science-based cartoons. And this was one that he did at about this time when there was all this discussion about what's with this redshift. And so you see on the far left, you see the astronomers huddled over the data, and they're thinking, ooh, well, maybe it's the Doppler shift, the strict Doppler shift. You've got some light source that's just barreling away from us at high enough speed that it is redshifted by 16%. Well, that didn't make any sense. Maybe it's the gravitational redshift. Maybe there's a supermassive body that's gravitational pull is so forceful that it actually changes, it alters the frequency of the light that it's emitting. That was something that Greenstein and Schmidt thought about a lot. Maybe it's the cosmological redshift with all of its attendant problems. And then you have this late-breaking bulletin running into the observatory. Wait, I think I found a new redshift. So it was a really serious puzzle. It was a puzzle that even the cartoonists in the world could make fun of and laugh at the lack of ability to solve this problem among the astronomers, the world's astronomers. So, well, let's just go back to this Hubble redshift thing, because that was the one that everybody kind of understood what the concepts were, how it was produced, and what it represented in terms of the objects that we look at in the sky. So if these redshifts were accurate, then the bodies that produce them must be billions of light years away, and also 1,000 times brighter than our Milky Way. They're bright enough to be seen from great distances, so they must be enormous. Maybe they're enormous. But some of them had short period variabilities, and by short period I mean like over a month. Now, when something varies in its brightness over a month, it can't be any bigger than a few month light years in size. Now, think about that in terms of our galaxy. We have 100,000 light years across compared to just a 1 month size. So these would be very, very tiny, very compact. What kind of things would they be? Some of them actually change their brightness somewhat erratically and rather rapidly. And so you could compare that with twinkling, the twinkling effect that usually are only produced by something that is small enough to be like a point source, considered a point source. But some of them are fuzzy, like 3C273. So they must be extended objects. Now, so are quasars powered by some unimagined energy source? Is there some better interpretation then that something that no one has ever thought of before that could explain these kinds of redshifts? It brings to mind the parable of the blind men and the elephant, where each individual is only able to observe and examine and determine something about one small appendage of the elephant. And so the guy that has the tail thinks he's got a rope. The guy who's got the ear thinks he's got a fan. The guy who's looking at the trunk thinks he's got a snake. There's no ability to actually make sense of the whole because their access to the information is so limited. And this was the case with quasars. There just weren't a lot of quasars that were known. And each one of them seemed to have these singular characteristics. So how can we put this together into something that makes sense, especially to make sense within what we already know about the stars and galaxies that are relatively near us. At the end of 1964, so just a couple of years after the discovery of quasars, there was a symposium held on relativistic astrophysics where this question came up over and over again. And Walter Sullivan, who was a science writer for the New York Times, wrote that the conference ended in an atmosphere of uncertainty and excitement. It was uncertainty because interpretation of the data just leads to conclusions that are hard to believe. Excitement at the possibility that a rare event in science may be at hand, the discovery in an utterly new kind of phenomenon that supposedly immutable laws are invalid. So, you know, you're on the brink, you're on the edge, you're either going to fall off the cliff or you're going to, you know, learn to fly, one of the others. So we had examples. Here's M82, not an uncommon and often photographed galaxy that's not that far away from us, certainly close enough for us to see its full extent and examine some things about its nucleus. But what was discovered was that there were actually quasars that were near it, and not only that, but they appeared to be moving away, or they were aligned in a way that it looked like, you know, they had been spit out or ejected in some way from the nucleus of M82. They had high redshifts. Why weren't there any blue? If something's being spewed out of a nucleus, why aren't some of the things moving towards us? You know, I mean, that was one of the problems with that idea. And then there were examples, there are quite a few of them, of clusters of galaxies, where you look at them on a photographic plate and you think, there are 5 galaxies close to one another. They must all be a unit, some kind of little family of galaxies. But when you do an investigation of their spectra, you find that there's a non-uniform, there's an anomalous redshift in there. All of the 4 of them all seem to be together and unified, and then there's this outlier that doesn't make any sense. So the question is this outlier just happens to be standing at the back, like way, 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 way back, but looks like he's in the picture? And so is it just an optical illusion? Stefan's quintet, that I'm sure most of you have seen photographs of this, maybe have even seen it in a telescope. 5 galaxies that look connected. For all intents and purposes, all of our photographs seem to look like they're all, you know, piled on top of one another with filaments extending into each other. But again, you've got 4 that are relatively the same, 1 that is completely different. And Seyfert's sextet, the same thing, but you have 5 the same and 1 that's different. So does this indicate that there's something peculiar about how galaxies develop in clusters? That they can all be in the same general area, but one of them develops aberrantly? No one could really know. Now, Jesse Greenstein, who had taken the first spectrum of 3C48, he was really bothered by this. I mean, it really nagged at him tremendously that there weren't any easy answers. Nothing, every time you answered in one direction, it brought up problems in the other direction. And so he wrote this little poem. Scientists are poets. Horrid Quasar, near or far, this truth to you I must confess. My heart for you is full of hate. Oh, superstar, imploded gas, exploded trash, you glowing speck upon a plate of Einstein's world, you've made a mess. Now, part of the reason for this, again, is because there just weren't very many quasars that had been identified. You didn't have a big enough collection to do a statistical survey that would make much sense, that wouldn't just find everything all scattered all around. And that was the case until Halton Arp produced his Atlas of Peculiar Galaxies. And that was in 1966. And one of the things that Arp did, because this was such a pressing problem to try and figure out about quasar redshifts, is he decided to look through his catalog and think, you know, you are probably all familiar with Herschel, and William Herschel, and his catalog of 2,000 fuzzy little objects that made it possible to kind of put them in little categories and compare their morphologies and their general locations in the sky and stuff like that. That's what essentially this Atlas of Peculiarities, Peculiar Galaxies, was going to give an opportunity to be able to develop a family of quasars. And so he went through the Atlas, and he found an interesting thing, that there were, in a number of cases, relatively close by peculiar galaxies. So you see those have their redshifts in the blue, with accompanying and sometimes clusters of quasars with much higher redshifts. And yet they looked so close. It seemed to ARP that this was beyond coincidence. This seemed to indicate to him the idea that perhaps these were in the evolution of galaxies, peculiar galaxies. Peculiar galaxies are radio emitters, basically. So these galaxies had something about them that when they were first evolving, that there was this atmosphere or environment that made it possible for quasars to also develop. And part of the secret of quasars was going to be uncovered if we could just figure out why they have such high redshifts. There must be some kind of physics going on that nobody's ever seen an example of before now, and we're going to actually be able to identify what that is if we study quasars very closely. Now, he presented this idea to his colleagues, of course, and yeah, you know, some of them thought this was really interesting, of course, but most of them said, you may have found a bunch of quasars and galaxies that have these characteristics, but you didn't find enough to make a good statistical argument. What if this is all just coincidence? Why does there have to be cause and effect or some kind of specific relationship? And an example of this kind of reasoning, imagine that you survey some houses in a town and you find that there are storks with nests on chimneys, on maybe many of the houses, maybe all of the houses, but some of those houses have families with newborns. So does it make sense to make a kind of a cause and effect relation between those two things? Because, I mean, you found quite a few examples, but did you find enough? Is it something that you can actually prove that there was some kind of cause and reflection? And of course, the majority of the astronomical community responded, no. And Harry Vanderlaan and Frank Bash said, you know, such statistical arguments are risky. They were very polite about it. But ARP found one example that he thought was the crucial experiment. This was the thing that was going to settle the thing once and for all. There was one of the peculiar galaxies, NGC 4319, relatively nearby, about 100, maybe less light years away, a million light years away. And so it was seen rather close on this photograph to a quasar, Markarian 205. And in fact, if you blow the photograph up, ARP was convinced that you could see evidence of a luminous bridge connecting the two, which meant that they might have different redshifts, but they were obviously so connected that they must be at the same distance away. He examined an isophotal image of this same pair, and there the bridge was far more distinctive and prominent. Not only that, but he saw some kind of physical connection between the two, that there was actually, they were having a physical effect on each other. And that was evidenced in this isophotal photograph. Now, when he presented these arguments, the American Association for the Advancement of Science decided, okay, it's reached this peak where we've now got seemingly hard evidence. We're going to host a debate. ARP is going to be able to present his arguments, and we'll get a representative from the community at large to argue their points against this. And so in 1973, there was a debate. The representative of the larger community, John Bacall, concluded with, seek and ye shall find. But beware of what you find. If what you have to work very hard to see something that you wanted to find. If you want to see a relationship between storks and babies, there's the evidence. It's right there, right before your eyes. But, you wanted to see that relationship. It doesn't, it's just purely coincidence. ARP, for his part, said, you need only one established case of a discordant redshift to force a crucial confrontation between observation and the current physics on which cosmology is based. In other words, if you find evidence of one black swan, you've disproved all of those ideas that were based on the idea that there could only be swans with white feathers. So you just need one hardcore example, and that makes your case. That's enough. That's sufficient. Not everybody bought into that, of course. A few years later, there was a big symposium in Cambridge, England, and a number of astrophysicists from around the world came. And one of the participants, Richard McCrae, drew this little diagram to illustrate, to represent the community and their reaction to this idea that there had to be some kind of newfangled physics that caused the redshift, the unusual redshift in quasars. I'll dissect this a little bit since it's a bit of a confusing diagram. Those who could see themselves in it knew exactly what he was talking about, by the way. But so there are individuals on the outside of this accretion disk. Note the resemblance to a black hole. And so the fashionable new idea is down there in the center, trying to attract everything around it. But it doesn't have any effect on these individuals. They don't have any interest in it. It doesn't change their view of nature in any way, and they go about their business. But others, maybe a little bit younger and more enthusiastic, see this idea and think, wow, I could incorporate that into what I'm working on. Or I can think of some tests to see if in fact this is something that will hold water or not. And they become quite interested and involved in the fashionable new idea. Of course, it always results in arguments and collisions, strong personalities tend to react with one another, and some of these collisions could produce some light, shed some light on the problem, maybe improve their understanding of quasars and so on. But most often it just ends up like you don't get tenure, or you don't get a promotion, or you lose access to instrumentation that you needed to continue your work. So there were damages involved in these collisions that got hard to repair in the end. But then and he was speaking of one person in particular, Halton Arp. There are some people who just go whole hog. They're just sucked into that black hole, and it becomes everything that they're involved with. They will never escape. And he was right about that. But this was how, looking at the scientific community or the astronomical end of the scientific community as a whole, this was how McCrae wanted to reflect the diversity in the. Now, this diversity is not visible to the public. The scientists surround themselves with facades. They all agree. There's nothing to see here. There's no problem. We don't have any arguments. We're all moving in the same direction, and that's because the majority prevails. The majority controls the editorial decision making in journals. They control who gets to make presentations at conferences. They hold the purse strings. So keeping that argument and dissension kind of hidden from public view is quite important. One of the elements of the purse string part of control over the dissidents in the community is, especially in astronomy, is the allocation of telescope time, especially on major instruments like Mount Palomar. You know, there are only so many minutes of dark, clear nights, and there are many, many, many more astronomers who want to use those minutes. And so every year, astronomers from all over the world submit applications to the Time Allocation Committee at Mount Palomar. And then the arguments begin, and the decisions have to be made, and control exerted over who gets to pursue their work and who is stuck with what they've got. Now, Arp had served on this committee for a number of years, and so he knew how it worked. He submitted his application in 1981, and he got the time that he had requested, which was really great for him. But the time that he got was accompanied by a warning that either you modify your research program and get off this quasar binge that you're on, or we're going to have to take action and control, restrict your time in the future. Now, this information leaked out to the public. Perhaps ARP did it, I don't know. But at any rate, the science writer for the LA Times, George Alexander, wrote several articles about this confrontation within the scientific community that he found quite interesting. I mean, taking away telescope time from an astronomer, he likened it to being disbarred if you were a lawyer, or having your hospital privileges taken away from you if you were a surgeon. This was a disaster. How could you do your work? There was just no way you could advance your program. And so he asked this very interesting question. How far from the mainstream of a given field can a scientist wander before he has effectively cut himself off from his colleagues? Now, we were soon to find out. 1982, ARP submitted his application, and he was accepted, but his time was drastically reduced. In 1983, it was cut off completely. And in 1983, the National Research Council published a discussion on quasars, on the current state of quasar research, and what it had found, what the conclusions of the community, the astronomical community, were. And here we see in black and white, or blue and red, there is at present no strong theoretical reason to doubt the cosmological nature of the observed redshifts, or to believe that new physics is required to understand these objects. That was that. If only quasars had turned out to be like, maybe a little different from the galaxies that we knew, the stars that we knew, but different enough to make life interesting, just not so different that they just completely flummoxed the whole system. If that had worked out, maybe they would have been a good thing, but as it was, they were a little weird and presented some problems. But nevertheless, the National Research Council says now it's time to begin looking at quasars as research tools, not puzzles to be further investigated. Worse than that, ARP and his quasar theories became the butt of jokes. The Journal of Irreproducible Results, I don't know if anybody's ever seen the Journal of Irreproducible, okay. And you know very well, this is a little publication that scientists and technical people often contribute to make fun of themselves or to make fun of other scientists. And in this case, this was an attempt to make fun of ARP and his idea that quasars are actually quite close. So this one contributor, Thomas McDonough, wrote a clearly well thought out proof that quasars are not only close, they're confined within the boundaries of our solar system. And they're all powered, they're so bright because they're powered by 100,000 light bulbs. Gary Larson poked his fingers in the eye of the Palomar Time Allocation Committee, in a sense. All day long, a tough gang of astrophysicists would monopolize the telescope and intimidate the other researchers. And so you see Halton Arp with that hand in his face, and those Time Allocation Committee people, they're giggling and laughing, these bully astronomers, preventing any outliers from getting access to the telescope. Worse than that, some members of the astronomical community started referring to Arp's Atlas of Peculiar Galaxies to Arp's Atlas of Funny Things. So, interestingly enough, Arp was not intimidated by any of this. They all just rolled off his back. And in 1987, he wrote, "I espouse here the Baconian principle of induction of general laws. It would seem obvious that if a scientist only reasons deductively from known laws, then he or she can never discover anything fundamentally new." Now worse, that same year, he published this. It's a book not written for his colleagues. This was not a scientific treatise. This was written for the public to learn something about this conflict that's going on and the treatment that people who have different ideas from the majority get from the profession as a whole. Well, the astronomical community was really pissed about this. And they were angry for a number of reasons, but largely because they like to keep these things quiet. They didn't, you don't want to take your dirty laundry and let everybody know about it. But it has the potential to introduce alien standards in the assessment of the problem. And that was something they felt that the unsophisticated public would not be able to bring the right kinds of reasoning to bear to help resolve the issue. Not only that, it would just probably more likely extend the length of the controversy. Now, every community has its nonconformists. A person who might be labeled as an eccentric in the astronomical community, maybe they're making observations that are like right at the edge of perception. Maybe they're using new instruments that people aren't familiar with, how to judge the quality of those instruments. But maybe things work out. And what they find and what they produce and how they produce it and how they argue it, it seems to give added value to the existing body of knowledge, introduces new questions, makes it possible to feel invigorated, and often ends up with some kind of acclaim at the end. You get additional funds. You get people signing up to be your graduate student, TA. Mavericks, on the other hand, that's a whole nother kettle of fish. These people pursue dead-end research. They're so eccentric, they don't even follow the normal rules. And it leads them to be isolated. They lose access to instrumentation. They lose colleagues. So, let me just... The maverick, seen from both sides. Scientific community viewed mavericks as self-serving dissidents whose closed-minded approach limits them to seeing only what they expect to see, and who waste valuable resources pursuing research based on unconventional and unsound ideas. The mavericks, on the other hand, see themselves as dedicated to uncovering the truth regardless of personal cost. They identify with historic pathfinders whose contributions were often misunderstood or maligned by their contemporaries. And they believe that they are forward-thinking, rather than the stodgy, closed-minded members of the conservative mainstream who can't understand or even accept the need for change. In 2002, Space Telescope Science Institute produced a little article. They had just captured a magnificent photograph of ARP's favorite pair of objects, NGC 4319 and the quasar Markarian 205. The best possible resolution ever achieved by photographic means, and they were convinced that, okay, you might think that you knew what it looked like, but here is the proof that this is what it looks like, and it proves that while they look like their neighbors, in reality the two objects don't even live in the same city. They are separated by time and space. Their apparent close alignment is simply a matter of chance. Now, ARP said, oh, okay. He took the exact same photograph and he enhanced it. And what he found was what he believed to be clear evidence of a bridge between the two objects. But he began to feel a little disappointed, more than disappointed. He was sad that not one prominent professional has now come forward to attest that the bridge is in fact real. In 2012, a new generation of astronomers who had launched their careers in the midst of the quasar controversy published a book that was a candid reflection on the past half-century of quasar research, along with their suggestions for its future based on a new standard model that treats these bodies as extremely luminous, active, supermassive black holes, a subclass of celestial objects called active galactic nuclei, or AGNs. So you see, these rotating black holes produce jets and have these surrounding accretion disks and so on. And you can, there's nothing in the universe that says all of these supermassive black holes have to be aligned like this. They're going to be in all directions, aiming in all directions. And so the reason for some of the diversity that we see is clearly because we're seeing different objects with different orientations, different kinds of energy coming in our direction. So we go back to the blind men and the elephant problem. As astronomers tried for decades to figure out the physical nature of Greenstein's horrid quasars, to finally understand how these objects fit into the grand celestial scheme. But like the blind man holding the elephant's ropey tail, their struggle seems to have ended with the realization that quasars are but one of several powerful appendages of the AGN elephant. Now, by the time of ARP's death in 2013, both he and the decades of controversy over quasar redshifts were quietly being written out of the scientist's account. And today, astronomers look to the next generation of instruments like James Webb Telescope. It's already making observations that will undergird or perhaps one day undermine the current standard model. As astronomers continue their journey down the road to quasars, we can be certain of one thing. They will continue to use the veil of the scientist's account to keep their messy setbacks and internal controversies safely shielded from public view. Meanwhile, you can also be rest assured that nosy historians will continue their efforts to lift that veil and expose the dissident views that sometimes hinder but always guide astronomers as they navigate the ruts, detours, and wrong turns along the way. Thank you. I don't know if we have time for questions or not. I kind of went on.
Repeat the question.
Oh, okay.
This is not a question, but a comment. It was, I think, possibly 1972. I was doing my graduate research at KC
Uh-huh.
while Art was there.
Is that right? Uh-huh.
Very delightful young.
Yes, yes. And you can tell that he has some real sense of self, that he's confident enough in himself that he really endured quite a bit of antagonism from his colleagues, and he endured it quite well, better than most, I must say. Yeah.
So where does it stand now? I mean, quasars are everywhere, right?
Yeah, yeah. Well, that model.
Gone.
There you go. That's the current view. And it hasn't modified very much since this was first proposed, just that we've been able to find more examples.
So ARP's catalog
Mm-hmm.
is still quite prominent, especially in
Yes.
interacting galaxies.
Yes.
Do we still talk about ARP at all, or is it just a vague name for a catalog?
Well, that's a good question. I don't know. I mean, when I was investigating some of this years ago, I interviewed one of the scientists at the Space Telescope and asked him about ARP. And ARP was still alive at that time, of course. And he said, "Oh, ARP. I used to try and come up with arguments all the time. I mean, he would come up with something, you'd say no to this, and he'd say, okay, well then what about this? No, what about that? What about the other thing? He said, I just don't even pay attention anymore. So I think that's kind of how he fell into the background, and I think that was one of the reasons why they were so angry about the publication of his popular book, was that it brought it into a realm of a new audience was made aware of the situation. Yeah.
Well, with all the discoveries now coming out of theories, the James Webb and all the other amazing telescopes that are all over the world, does the scientific community have this kind of animosity towards new theories like they did back then?
Well, back then wasn't so far back then. Yeah, right. Yeah, I think they do. And there are some, there's a fellow at Harvard, and I can't think of his name, but he comes up with some very unusual ideas. And so people would just sort of walk away and change the subject or something rather than attack people, maybe, but that's a good question, and I don't know that and Tom's question about where ARP stands today. I think now that he's dead, it's safe to talk about him without feeling like you might incur some wrath from. But one of the fellows who was involved in the writing of this book, Jack Sulentic, was one of ARP's most ardent supporters. He was a graduate student under ARP. And really had a great deal of sympathy for the kind of work that ARP did, but even I think he welcomed this production of this new model, which helped to explain why. I mean, you could see why ARP thought what he did, and so that helped to explain things to people that didn't mean that he was nuts. You know, he's not just a kook. He was an extremely accomplished astronomer. So, yeah.
That doesn't serve the controversy not so much with ARP, but all things in science or in public view, such as our current thing with climate change, another one is vaccines.
Right.
All these things, if it doesn't follow a particular viewpoint, then one, we're going to suppress you because we want funding.
Right.
Funding is number one, all the money, every single time. And whether it's a new idea or a bad idea, time will resolve that.
Right.
Discovering new things.
Yeah. Yeah, with respect to vaccines, the people who survive will be the ones who write the account. Yeah, that one. Well, and even with climate change, the survivors are the ones who write the account, and whether it's a physical survival or just intellectual survival. But yeah, that's really true.
That's one of the side points
Yeah.
of publication. You've got to publish to get your grant.
Mm-hmm.
You can't publish because the reviewer says, I don't agree with that viewpoint. Your career's over, right? That's kind of the way it is.
2 on 1 here. So 1, 2, 3.
Okay.
Go ahead.
What do you think can be done to kind of shed light on what the scientific community is keeping to itself and enhance public understanding of what's actually happening?
Go to conferences. You know, when they publish proceedings from a conference, you don't find out who's out in the hall talking about somebody instead of with them. You don't know who went to coffee with who, you know, and they don't publish usually the question and answer period where sometimes in these sessions people can be quite abrupt and rude in their asking of their, you know, like, you idiot, why do you think, you know. So those things don't get published and aren't aware, you know, the public never gets access to that. But if you attend to some of these conferences, you may get a wider sense of what people say in the background noise of the actual official events that are going on in the proceedings. But visit a science, go to Space Telescope and talk to the people. You know, they usually, if they're free, they will talk to you and answer your questions. But I think, yeah, it's hard to gauge. It's hard to gauge unless somebody writes something for public consumption, and then you have to understand that you're just getting their point of view. It's hard to tell.
Thank you.
Mm-hmm.
So I really liked how you were talking about the maverick and the innovator.
Mm-hmm.
He's obviously a maverick.
Right.
That each individual is obviously the innovator.
Yes.
So can you say something more about maybe how these individuals that were maybe influenced, not influenced, how did they learn to maybe change their behavior, or was that even thought about? Do you have any insight into how they were able to get this accepted now, where his stuff maybe was questioned so much?
Well, I don't know. I think to some extent it is a luck of the draw in a way. If you had done some investigation that showed maybe a slight variation with accepted views, but led to something that sparked an idea in somebody else's mind that seemed to, you know, be productive. But if it was something that seemed too off the wall, or if you were somewhat timid about your professional advancement, and you saw those around you poo-pooing the work that was done, you might be more inclined to kind of jump in with them rather than be seen or caught with. Jack Salentic is a good example. I mean, it was very risky for him as a graduate student to follow art because it meant his career options were always tainted by the fact that he had art as an advisor snapped onto his CV. And so when people are looking to hire somebody, who knows, maybe Jack Salentic is another one of these wackos who's going to just, you know, use our time and be a problem. So it's hard to know how to go through life.
Thank you.
Yeah.
So the active galactic nucleus explanation for quasars.
Mm-hmm.
When did that come about? When was that idea first popularized?
Oh, well.
How long had AGNs been on the astronomy radar, so to speak, before they got proposed as a descriptor of quasars?
Yeah, well, when I was teaching that introductory astronomy class, all of these things were sort of just popping into the news, these secret galaxies radio regions, which were probably among the older ones, the BL-Lacerti objects, and these are optically violent variables, I think. Liners are low ionization nuclear emission regions. So all of these things were starting to be identified, but they were seen as different things, and maybe not necessarily connected. And so this unification was something that happened somewhat gradually, but the idea that quasars could be included in this was something that was just beginning to, I think, about 2010 or something like that, to come into view. I'd have to check and see when that the first suggestion of quasars as members of this, but I think it was beginning to be to emerge at about the time that this book was published. All the people involved in the production of this book in 2012 were people who, sort of like the generation that grew up with Sputnik. They never knew a time when there weren't rockets going around and satellites and stuff like that. People who grew up at this time, the early Viking missions and so on, never knew a time when there weren't spaceships going off to other planets. And so their ability to envision new questions and see different models is quite different from people who lived before and didn't have that as an option. But I'd have to check and see when quasars got linked in specifically. I'm not sure it was a specific.
When was it AGN first proposed?
Have to look that up. Just Google it. Ask AI.
That's one in the back.
Yeah.
Okay. So when did they start using digital cameras? Because you're using all those glass plates from the 60s and the images are just so bad compared to what we have now.
Yeah. Well, that's another thing you'd have to look up when and the problem, of course, is converting old instruments into the new technology. It takes time and training for people to understand how to use them. Now I see these photographs that get posted on the Chaos website that get emailed out, people with these little sea stars. And you see images of the Orion Nebula. My God, it looks like something that was taken from Palomar. It's just phenomenal. But it takes time for those transformations to occur. I don't know when that happened. You got a follow-up question?
The early images are so bad.
Yeah. Well, they were all we had. That's why you took multiple ones. I mean, Schmidt explained that when he took the first photo of the spectrum of 273, he had no idea how long to expose it, and so he way overexposed it. He didn't realize how bright it was, and so he had to take multiple to finally get one that showed the lines with some clarity. And so it's trial and error. And you work with what you got.
Thank you, Barbara.